All right. So first of all, again, welcome to everyone in the LambdaConf. I know, unfortunately, I could not make it in person, but I'm super excited to be presenting today around the topic of fine-tuning large language models with declarative ML orchestration. And just a quick introduction about myself. I'm Shivay. I'm a WasmEdge ambassador, and I'm working at Couchbase as a developer relations engineer. And you can connect with me on @howdevelop. So today we're going to be talking about a very relevant topic, which is how do you actually fine tune large language models, and how do you do it in a more cost effective manner, given the fact that today so many large enterprises are leveraging these large language models and they use a lot of compute power. It's very expensive to actually do the inference, do the training of these large language models. So how do you do it in a way that is actually also economically feasible, and also at the same time when it comes to productionizing such kind of system, how you can leverage declarative machine learning orchestration or declarative infrastructure in order to actually enable you to do that. So today, of course, the first thing that we'll cover is why to actually fine tune large language models in the first place. What are some of the techniques that you can actually employ or you can leverage in order to do the fine tuning? Then what exactly is, how do you actually enable to do this fine tuning in an effective manner with declarative infrastructure? That means leveraging your infrastructure or the infrastructure provisioning to be very efficient in order to be able to do fine tuning more efficiently and a more cost effective manner. And how you can leverage an open source tool like Flyte in order to do this fine tuning. So we'll cover all of this today in today's session. So let's get started. Now, of course, the first point being why actually fine tune large language models in the first place. So, of course, now considering a typical use case, now you would usually give an input or a prompt to a large language model. And for those folks who don't know what is a large language model, it's a highly specialized deep learning based model that has been trained over a lot of data. So classical examples of large language model would be something like a GPT-4, GPT 3.5, Gemini, and on the open source side of things, we have models like Llama 2, Llama 3. All of these models are really large models that have been trained over millions and billions of different type of items. So these are all, of course, text-based, or some of them are also multimodal models. That means they interact with both text and images alike, or different types of input data. So normally, if you give it a prompt, the LLM will give you an output or a response. So that's a general way in which an LLM operates. Now, uh, during this entire time, ever since ChatGPT came into the first place, essentially what we came to notice was we had this rise to something known as prompt engineering, which essentially means that you are adjusting the input that you're giving to the LLM, and you are really just kind of fine tuning this input in order to make it more optimized while still keeping the model waist fixed. That means you're not really changing the structure of your entire model. So the model as it is, it will remain the same, but you're just adjusting the given input to make it more optimized to get the desired output. Because we have seen that if you give a very vague kind of an input to ChatGPT, it will give you a very random answer. So it's all about optimizing your own input that you're giving to the model as a prompt. And that is why like we have like actual specialized courses just around uh, prompt engineering that allows you to give more specific prompt to the LLM so that it can give you a desired output in your desired format. But that's a bit towards the prompt engineering. It has nothing to do with changing the weights of a model. And by what do we mean by weights of a model? So weights are nothing but they are really just the building blocks of any AI inferencing. So the weights carry the information about the input, about all of the training that has been done. So they are essentially the building blocks of any AI system. So whenever we say that there are weights, that means that an AI model has been trained over some data, and then these models carry some numerical values that contain the information behind the training. So that is prompt engineering, right? So that's the prompt engineering. Now, what is prompt tuning? So essentially, prompt tuning, what it actually means is that we are taking, like, let's say, a number of different tasks, and we have prompts for all of these different tasks, and we just essentially keep on holding them, and we have this input embedding layer, which we kind of update in order to get again more desired responses. So it's more to do with the fact that all the inputs that you're giving to your model, you're just kind of fine tuning those inputs to get the desired output. Again, this is not really changing a lot of the model itself, which we will explore further when we are fine tuning the model. Now, finally, let's talk about the actual fine tuning, which means that we update the weights of the model based on a specific data to get desired behavior. And this is really important in the context of large language models, because a lot of times, something that you actually might have heard, that large language models are trained over such a large amount of data. And a lot of times they might not have the latest or the most updated data, given the fact, for example, GPT 3.5, which if you're leveraging the free version of ChatGPT, only has been trained over data till 2021. And like the later versions have been trained till 2023. That means any data that comes after 2023 in the 2024, like let's say, the AI model will not be able to actually answer questions related to it. And that's where we essentially fine tune the model. That means we are updating the model weights with a new set of data so that it can actually give you desired outputs or desired results based on that particular data. Some of the techniques are also known as like retrieval augmented generation. These are some of the techniques that you will actually learn about, or you might hear about them. So fine tuning is all about just updating these model weights so that they can give you a more desired output from, or you get a desired behavior from the actual model. Now, what are some of the pros and cons of both fine tuning and with respect to prompt engineering? So, of course, when it comes to prompt engineering, we are really just updating what input we are giving to the user. We are not really requiring any machine learning or data science and expertise, because, of course, here it's all about making your input better so that the AI model actually understands your input better and is able to give you a better result. But of course, the biggest con over here is that in case your model has not been trained over the right kind of data, or it is lacking in certain type of data that you wish the model to be worked on, then of course it will always give you poor results. Whereas with fine tuning, you get control over the training and the inference data, and that means it can be more specialized to do specific tasks. For example, today there are a lot of different tasks such as creating AI agents that essentially train over your own documentation website, and then they only give you responses based on your documentation and do not give you responses outside of that documentation. So that's one of the use cases of fine tuning, where, like, let's say if you're building an AI bot for your own documentation site and you want the responses to be just limited to your docs, so you can fine tune the AI model, in this case, like let's say a GPT 3.5 or a GPT 4 model over your own data, and then you can fine tune it in order for it to work on just that data. But of course, this requires you to have ML expertise, and you would need GPUs because you are essentially retraining your model in order to fit it better, right? So of course, you need GPUs and higher compute power. And then, so this is like, kind of an example where with fine tuning, you need ML skills. With prompt engineering, you don't necessarily need engineering skills. You just get better results with, making your prompts better. So that's an use case for the prompt engineering. And here are some resources if you're interested in prompt engineering. Of course, today's session is not about prompt engineering, but I just wanted to quickly differentiate between the two different topics, because of course, it might be, there might be a question about, hey, like, how is prompt engineering different, or how does it differ than fine tuning techniques? So I hope that with this particular overview, everyone, is able to understand that what is the use case for prompt engineering. So that is the main idea behind about prompt engineering versus fine tuning. So of course, the reason or the rationale, as we have kind of covered, right, is that when it actually comes to fine tuning, like, the reason is to make the AI models, or to essentially take a base model that has been, and then to specialize it over a specific data distribution. And how do we do that? By adjusting the weights. And this practice is valuable where data privacy is really important. So you want to train it over very specific amount of data. So now let's understand that how do you actually fine tune the model in the first place. So we essentially have two different ways primarily. We also have something which is the human feedback, but we'll talk about that a bit later. But we have essentially two different types. One is the continued pre-training, which is also a short form for CPT, and the supervised fine-tuning. So with continued pre-training, essentially what it means is that we are extending the pre-training on an additional set of tokens. So tokens here are nothing but just your input data, input vectors, specific to your problem set that you're trying to solve. And then supervised fine-tuning essentially means that we are providing examples of the desired task that we wish to accomplish in the form of a prompt and response based data in order to make our LLM feel a little more like a chatbot. So wherever you are having use cases where you're dealing with like a chatbot, so whenever you're dealing with like some kind of a prompt and response, that's where we have supervised fine tuning kind of technique. And of course, like the continued retraining is more to just pre-train our existing data over a set of tokens that is dedicated towards a specific data set that you have prepared for yourself. And finally, we have something which is called as RLHF, which is essentially a reinforcement learning based on human feedback. So essentially using the human preference data to train a specific model, we can generate results that are more closely aligned with the human expectations. And it's based on the supervised fine tuning because you're supervising the AI that, hey, like this is the human preference and this is how you should act on it, right? So that's the entire idea behind the fine tuning with respect to the RLHF, which is the reinforcement learning based on human feedback. So I hope this makes sense to everyone. Now, of course, when it comes to like some of the methods, when it comes to like training large language models, because of the fact that they require you to have a lot of compute power. So some of the techniques are things like gradient descent. Then we also have like model parallelism, where you would basically just have essentially multiple machines, like multiple GPUs, and you just divide your model weights into the different GPUs, train them over each and every single GPU, and then finally retrain them, right? Then you can also actually use things such as optimizers and schedulers in order to actually train your models faster, or use a technique like data parallelism, where you divide your data and essentially train your different sets of data on different GPU devices. And then you can always then take those input weights that you have on all of these different devices, and then combine them together to have your essentially your trained data sets based on different data sets that you had. So you can use techniques like these model parallelism, data parallelism to train your AI models faster, and they are also generally more cost effective. Now, talking about some of the techniques that we have with respect to fine tuning. So the first technique is zero redundancy optimization. So this essentially takes ideas from both the data and the model parallelism, and this allows you to basically share these model weights. So rather than running your entire model on just one single device, you're breaking down your entire model weights into different devices. So like let's say different GPUs, and you share different weights on different GPUs, and then you can basically proceed with a forward and a backward pass. So basically, you forward passes that once you have done training in one layer, you move the model to the next layer, and then you can always move it backwards in case you want to do some optimization techniques. So this takes use case from the model parallelism. So of course, this allows you to train your model in a more efficient manner and actually not be dependent on a single device, which actually increases the workload of your AI model inferencing. Now, there are some, of course, some more optimized techniques. So the other one is called as 8-bit quantization. So 8-bit quantization is literally nothing but we are essentially reducing the memory requirements. So consider that if you have like a 64-bit number, you are reducing it, or a 32-bit number, but you're reducing it to an 8-bit number, right? So of course, you're essentially reducing the footprint of the model itself. Now, the question might arise that, hey, if we are reducing the size of the model, does that mean that does it affect the performance of the model? So more often than not, it actually does not. We are just reducing the mathematical concept of like using a 32-bit number and reducing it to 8-bit. Similarly, we are reducing the size of the model, but it still actually retains all of the capability of the model. So that means that the weights are still there. You'll get similar responsiveness from the actual model itself. And this can actually, lead to better optimization and faster processing of your model. So like, this way, it allows you to fine tune your model faster and do it more quickly in a more memory intensive or memory efficient way. And finally, like, and just in case if you're interested to see like how do we actually do this 8-bit optimization, so here's like a Google Colab notebook, and I'll be sharing the slides for these particular optimization techniques. So here we have basically like first of all taken our input vector, and we go ahead and run our quantizer 8-bit, which reduces your input vector into that 8-bit quantization. So this is a notebook that kind of does that. So I'll make sure to share this with everyone. Now, the final technique that we have is basically known as LoRa, which is a low rank adaptation. So this allows us essentially to again fine tune large scale models in a more memory efficient manner. So idea over here is that we only update a small part of the model weights, specifically targeting those that have the most significant impact on the actual on the actual task at hand. And this like approach again makes it more efficient to again keep just optimizing only those parts of the program or those parts of the weights that are actually responsible for delivering the end result. So this way you save up on a lot of the compute power rather than basically updating all of the weights. You're just updating very selective weights that are actually responsible for the use case that you're trying to build. And here is like a notebook on how you can actually achieve LoRa. So again, feel free to have a look once I share the actual final discovery. So now, coming to the use case that, okay, like we have understood that fine tuning is responsible. It's important for being able to make your model weights more efficient and just make your AI model more efficient for a particular use case. Now, of course, when it comes to like doing all of these fine tuning techniques, they are very cost ineffective, right? Because you have to run large GPUs at all times, and it ends up costing a lot to organizations. So how can we make it such that you can do this in a more cost-effective manner by giving the provisioning of the infrastructure in a more efficient manner? That means that only provisioning a specific amount of compute power and only for specific times, right? That's what is the main use case over here. So essentially what orchestrators are, they just coordinate the logical flow of compute to get from your raw state to your desired state, right? And that is why essentially orchestrators allow you to determine how much amount of compute you actually need for your workload, right? What all dependencies that are there with your workload, they carry all of that information. And this is required considering that, for example, not every step of your AI workload will require the same amount of compute. Perhaps some aspects of your compute might require less amount of compute, whereas some parts like training and fine tuning require you more compute power, right? So how you can efficiently distribute your infrastructure to just work on specific tasks. So that's where orchestrators really help you. And that's where Flyte, which is an open source production grade machine learning and data orchestrator, comes into picture. And you can leverage Flyte in order to do that. So essentially, Flyte, what it does is that it takes your entire AI system and breaks it down into different tasks. And depending on the resource consumption required for a specific task, for example, fine tuning can just be a task. You can actually define at that task level how much amount of compute do you actually want. And there can be multiple tasks that you can have in your entire orchestration in your workflow. And then workflows are just multiple tasks stitched together. For example, you could have one task on just input data cleaning, and then one task on training, and one task on finally like doing some testing. And workflow will be combining all of them together. And then similarly, like what, one of the use case, one of the use case over here is that with Flyte, what you can actually do is that you can define at a task level how much amount of compute do you actually need, right? So you can actually do that. And you also can write these workflows and tasks in multiple languages, like in Python, in Java, and at the same time, they are also type safe. So you don't need to be worried about, all of that. And then, of course, as I mentioned, that at every single, input for every task, you declare, using ephemeral clusters, you declare how much amount of memory and how much amount of CPU and GPU resources you need for those specific tasks. And since Flyte runs natively on top of Kubernetes, it actually helps you to accomplish that. So I'll just quickly show you a quick demo of how this actually runs. So here, I'll just quickly share my entire screen to quickly showcase how this is actually running. So I have a recorded demo. Here, what you can see is that I have this particular cluster where, what you can see is that I have this cluster defined over here, which is a task. And over here, you can see that how much amount of nodes do I want, how much amount of memory, GPU, and CPU power that I need. Then I have defined a specific task that allows us to basically do the fine tuning. So this is the workflow that is essentially doing the fine tuning. And here you'll also see that we have something known as deep seed, which is essentially responsible for doing the zero fine tuning, which is the zero fine tuning technique. And here, what I do is that I just run this particular optimization technique over, the Llama 2 model that I'm running. And then what I do is that as soon as I run this, it basically opens up this UI where you can see that all of the different tasks that I have, which are training the model, then quantizing the model. Quantizing is a technique for fine tuning, and then saving that particular model to Hugging Face. All of these particular tasks run in a sequential manner in a DAG-like structure, which is a directional acyclic graph. And you can see that in a graphical format as well, where all of these particular workloads are all connected with each other. And of course, as I mentioned, that you can use declarative infrastructure to do all of this provisioning at that particular task level, which of course, as an example over here, which is like the training technique, we defined how much amount of memory, CPU, and GPU resource we need, right? So that's an example of the declarative structure. And now I'll quickly go back to my screen sharing. So over here we have, so I'll go back to my slides now. And of course, you can also have specific dependencies that might be required for a particular task. You can also define those inside of your code base as well with the help of Flyte. And you also get more amount of data persistence. Like you don't have to worry about the serialization and the deserialization of your data. All of that is taken care with the help of Flyte. And of course, like that's where, the fine tuning workflow came. This is the workflow that I just showed in that demo, where you are doing that particular fine tuning. So that 8-bit quantization is running as the workflow. And all of this can be done very efficiently with the help of Flyte, where you do that infrastructure provisioning for every single step. And that allows you to save of cost and just be more efficient. Right. So that is the demo that I just wanted to quickly show you with that we ran with Flyte. And here are some of the resources. So this is a Flyte docs and all of the different notebooks that were covered in this particular doc. And of course, with that summary, like if you are basically caring about building applications and you don't want to do any fine tuning, then prompt engineering is better. But of course, fine tuning allows you to do making your large language model more efficient for a very specific use case that's focused on your own data set. And then we covered like the different type of optimization techniques. Each one of them work well with different kind of use cases. And Flyte is just providing you that orchestration platform that allows you to very easily just define your machine learning workloads. And you don't have to worry about the resource requirements and infrastructure. All of that can be provisioned on the fly by defining them as Python functions. And it also connects with multiple types of open source ML tools like transformers, Hugging Face, that allow you to very easily not only fine tune your models, but then deploy them on things like Hugging Face or any other model registry artifact. So that's a quick summary of what I wanted to cover, but now I'll be open to questions. Thank you so much.